Okay, so we've been talking a little bit about exponential functions and some kind of exponential growth and decay. Now what we're going to do is we are going to be looking at solving some exponential equations. So this is 7.2. We did not do 7.1, and that's okay. Um, but we are going to be looking at some 7.2 stuff. Okay, here's a warm-up for you. Go ahead and give this a try based on what we've done the past couple of days. Pause and come back when you're ready. A population of bacteria triples each day. The population starts with 500 bacteria. Write an equation for the population of bacteria as a function of the number of days that have passed D. So we're writing an equation and we're told that the bacteria triples each day and that the population starts with 500. So if you recall, when we were looking at these previously, when we would have our population would be equal to 500, that's kind of our initial amount. And then remember, we're going to multiply that 500 by 3 each day. So D would be the number of days that go past. So we'd have 3 raised to the D power. For the second one, the growth of population of rabbits is given by the equation below. P of T is equal to 3,000 times 1.06 to the T power. First question is, what is the initial population? That would be 3,000. So if T was 0, this would just become 1, or the 1.06 to the 0 power is 1, so it would just be 3,000. What is the multiplier by? What am I multiplying by every time? 1.06. At what rate of change is the population changing? That's a great question. What rate of change is the population changing? It's 1.06, but really it's 0.06 is what it's changing by, because the 1 is just the current population. And what will be the population after 3 years? Well, we could plug that into our calculators. 3,000 times 1.06 raised to the third power. You can just go ahead and plug that into your calculator. Okay, so in exponential equations, the variable occurs in the exponent. Okay, so one way to solve such exponential equations is to rewrite the two exponential expressions with a common base. Until we learn another skill dealing with something called logarithms, that will come later, we are going to just create common bases. So let me show you what I mean by that. I have here for number 1, 3 to the x power is equal to 9 to the 4th power. I don't know what x is. However, could I rewrite 9 as having base of 3? So rewrite this as 3 to the x power is equal to, well, 9 is 3 squared, so this would be 3 squared to the 4th power. Or 3 to the x power is equal to 3 to the 8th power. Okay, remember our laws of exponents tell us power to power you multiply. Okay, so it's pretty clear to me here from this step that x has to be equal to 8. All right, so once we get these bases to be the same, then we can set the exponents to be the same thing. So x has to be equal to 8. All right, for number 2, a little bit different because now we're dealing with some additional information other than x. But again, notice here's 2, this is 4. Can I change 4 to have a base of 2? So this would be 2 to the 5x power is equal to, I'm going to change 4 to 2 squared to the 2x minus 1 power. So if I have 2 to the 5x power is equal to 2 squared, again, power to power you multiply, so this would be 2 to the 4x minus 2. And now what we can do is, since my bases are the same, I can set my exponents to be the same. So 5x has to be equal to 4x minus 2. And if I subtract 4x from both sides, I get that x is equal to negative 2. All right. This third one, again, a little bit different yet. I have 4 and I have 64. So I can change 64 to a power, or 4 to a power, or base 4. So I'd have 4 to the 2n minus 1 would be equal to 64 is the same thing as 4 to the third power. So I could set these two things equal to each other. Oops, I circled the whole thing. I just meant the exponent. So I have 2n minus 1 is equal to 3. So 2n would be equal to 4, or n would be equal to 2. Now, just a side note on this one, I could have actually changed both of these bases to be base 2. So I could have written this as like 2 squared to the 2n minus 1. And then I could have had that equal to 2 to the, that would be, I think, 6th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So then this would have been 2 to the 4n minus 2 is equal to 2 to the 6th. So 4n minus 2 would be equal to 6, and you could solve from there. Okay, go ahead and give these ones a try, however you so choose. Pause the video and then come back when you're ready. Okay, so for part A, I'm going to go ahead and change 64 to have base 4. So 4x is equal to 4 to the third power So 4 to the x power is equal to 4 to the 9th. So x has to equal 9. Okay, over here, I'm going to change the 9 to be base of 3. So I'd have 3 to the 2x power is equal to 3 cubed, oops, not cubed, 3 squared to the 5x minus 4. So I'd have 3 to the 2x power is equal to 3 to the 10x minus 8. Power to power, we multiply. So setting my two powers equal to each other, 2x is equal to 10x minus 8. If I subtract 10x, I have negative 8x is equal to negative 8, or x would be equal to 1. Now, we can always check our answers on any time that we have equations by just plugging those numbers back in up here. So if I were to plug this in, I would have 3 squared times 1 is equal to 9 to the 5 minus 4 power. So 3 squared is 9, and this would be 9 to the first power, which is 9. So you can always check it off to make sure that it actually works. Okay, so let's deal with a couple of word problems, and then we'll be done for today. Exponential functions can take the form of this, which we kind of looked at previously. A times b to the x power. So a is the initial amount. B, on the other hand, is the multiplier, okay? And x is our input, y is our output, okay? So if the b value is not given, you might have to solve for it, and we're going to solve for it using kind of what we did previously, okay? So what we'll do here is I have this example. Write an exponential function for a graph that passes through the points 0, 5, and 7, 200. Okay, so 0, 5, and 7, 200. Well, we are going to have kind of, if we were to sketch this graph, it'd go through a point here at like 0, 5, and then also over at 7, like way up here at 7, 200. So it's going to look something like that, okay? Now, what's the starting initial amount? So basically, when x is 0, what is y? Well, it tells us that within the context of this point. So I would say y is equal to my starting amount, a would have to equal 5. Okay? Times b, it doesn't tell us b, and we don't know necessarily x. Now, I don't know what b is. I don't necessarily know what y and x are, but I do have this extra point that I could plug in to use to help us to solve for b. So that's what I'm going to do next. I'm going to use 200 for y is equal to 5 times b to the 7th power. And now we're going to work to solve for b. So I could divide both sides by 200, or sorry, not by 200, by 5. And I end up with 40 is equal to b to the 7th power. I'm going to come back up here. So if you have 40 is equal to b to the 7th power, how do we undo taking something to the 7th power? Well, we 7th root it. So use the 7th root. This is good review for us from past chapters when we were using different roots of different indexes. Okay, so b is going to have to equal the 7th root of 40. And you can actually just leave your answer like that. If you had a calculator, you could plug that in, but you don't need to. So y would be equal to a, which was 5, times b, which is the 7th root of 40, to the x power. That would be your equation. Okay, if you were using your calculator, that 7th root of 40 is about 1.69. So another way that we could write this is y is equal to 5 times 1.69 to the x power. Okay, now this is a word problem that is a little bit different because it doesn't actually just give us points, it gives us some context. So we're going to have to create the points. So in 2000, the population of Phoenix was 1,321,045. By 2007, the population of Phoenix was estimated at 1,512,986. So part A is to write an exponential function that could be used to model the population of Phoenix. So the tricky part here is to let x be the number of years since 2000. That way we're not having to plug in a whole bunch of like 2000 and 2005. You could do that, it wouldn't be wrong. The biggest thing is that you just have to be consistent. So I'm going to go ahead and create 2 points. So I know when my x value is 0, okay, so no years since 2000, that would be the year 2000. So that'd be our starting year, which is 1,321,045. The other point that they tell us is in 2007, so when I'm 7 years past 2000, so x would be 7, I'd be at 1,512,986. Okay? Now, when we go ahead and to write the equation for this, we're going to use the same process as last time. There's just bigger numbers, so you're really going to need a calculator for this one. So for part A, I'd have y is equal to my starting value. Okay, so my A value would be 1,321,045 times b to the x power. I don't know what b is. I don't know what x and y are, but I do have an xy point that I can plug in. So I'd have 1,512,986 is equal to 1,321,045 times b to the 7th power. All right, I promise they're not always 7th powers. Just these 2 examples. Okay, so now we have to work to solve for b. Again, the numbers aren't pretty, but we can do it, especially if you have a calculator. So we're going to divide each side of the equation by 1,321,045. And when you do that, on this left-hand side, you get about 1.15 is equal to b to the 7th. So I could then take the 7th root of both sides. So b would be equal to the 7th root of 1.15. Okay, which is about equal to 1.02. So my equation is going to be y equals 1,321,045 times 1.02 to the x power. There is an answer to part A. For part B is asking us then predict the population of Phoenix in 2017. So that means the x has to be 17 because we're 17 years past 2000. So I'm going to take that x is 17 and I'm going to plug it into this equation down here. So I'd have y is equal to 1,321,045 times 1.02 raised to the 17th power. All right, raised to the 17th power. Now, when I plug that into my calculator, I get out something interesting. I get out that y is equal to 1.84978 E6. You, depending on the setting on your calculator, might get something slightly different. I want to remind you, we talked about this back when we did our calculator workshop at the very beginning of the year, so you may not remember. That E is scientific notation. Okay, so what this really means is it really means 1.84978 times 10 to the 6th power. Okay, times 10 to the 6th power. So that E is just basically taking place of that times 10 to that part. Okay, so if we were to go ahead and deal with this, I want you to write your answers out as numbers, not in scientific notation. So a reminder, scientific notation just tells us how many spaces I need to move the decimal point. So I move the decimal point 1, 2, 3, 4, 5, and sometimes you need to add a little extra. So the answer to this question would be 1,849,780. So 1,849,780. And this is the population, so this would be people. Okay, now you can always just go ahead and double check with this and make sure that it actually makes sense. So I'm looking, my growth from 2000 to 2007 was about 200,000 people. So in 7 years, about 200,000 people. So then in an additional 10 years, it makes sense that we'd be adding about another 3,050 people, or 350,000 people. Okay, so I think that that is a reasonable answer. All right, here's your homework. You guys should have some extra time, so I want you to get started on this in class, and then anything that you don't finish, work on at home. I will be back tomorrow, so I can help you with whatever you need. Have a great day, and I will see you tomorrow.